In this video, we will continue with chapter 10 on exponential and logarithmic functions, and we will look at section 10.2, which is natural exponential functions and the problem of growth. So how is the number e defined? Just write that. How is the number e defined? So remember, at the end of our previous video, we said e is our preferred base for exponential functions. So suppose we have the function f of m is equal to 1 plus 1 over m to the power of m. This is a simple growth function. So what happens if m increases? If f of 1 will be 1 plus 1 to the power of 1, that is 2. If f is equal to 2, it's 1 plus 1 over 2 squared. That's 2.25. If f is at 3 is equal to 1 plus 1 over 3 cubed. That is equal to 2.37037. F of 4 is equal to 1 plus a quarter to the power of 4. That is equal to 2.44140,625. So in your own time, you can calculate what is f of 5 and f of 6. So as m increases, f of m approaches e. That means e is equal to the limit as m approaches infinity of f of m, or the limit as m approaches infinity of 1 plus 1 over m to the power of m. So what does the Maclaurin series of e look like? So we have e to the power of x is equal to 1 plus x plus 1 over 2 faculty x squared plus 1 over 3 faculty x cubed plus 1 over 4x 4 plus 1 over 5x5 plus the rest. So if x is equal to 1, e is equal to 2.7166. This is up to n equal to 5. N equal to 6, e is equal to 2.7180. N equal to 7, e is equal to 2.71825. So e, our natural base, is equal to 2.7182819. Please note that most calculators will have a function for this. Okay. So what is the economic interpretation of e? The first one is that it's our mode of compounding interest, and the second is it's the mode of growth. Specifically, it's our instantaneous rate of growth at any point in time. But we know that growth does not take place continuously. So for example, we have discrete periods of growth. In this case, our growth will be approximated or will approach e to the power of RT. We also have periods of negative growth. Here, our exponent is simply negative RT. So let's do an example. So say we have V is a value invested. A is the initial amount invested. R will be our interest rate, our real interest rate, and M is our yearly, yearly compounding period, and T is the number of years or time that it is invested. So we have our function Vm is 1 plus R over M to the power of mt. This is if W from our previous period is M over R. So what happens to this function? So Vm, if W is equal to M over R, is equal to 1 plus 1 over W times W RT. What does this function remind you of? Simply our exponential ART function. I haven't written that down. Okay. So this function, Vm, it's this f function. So you see it looks the same. So this will be equal to the limit as m approaches infinity of Vm will be equal to AERT. So this is your function if interest is compounded continuously, and this is discrete growth. Please look at the examples in the textbook. One more thing I want you to note. For example, if you get interest at the end of 6 months, M will be equal to 12 divided by 6, which is equal to 2. At the end of 4 months or termly, 4 months, M is equal to 12 divided by 4, equal to 3.